Hi, Norman. How's it going?
Pretty good.
All right.
Pretty good. I don't know how they expect us to keep up with our schoolwork while going to clean out our dorms. I have to drive back down to Florida tomorrow to clean out my dorm.
Yeah, it is, and it's rather unexpected. And you know, it's kind of it's unexpected in the sense that they didn't like give an idea as to when they were going to make a decision. So at least you could plan. One thing, excuse me, I'm fine. I just I'm a little dry. Um, One thing I will do is I'll be more than happy to give extensions on anything because we're all going through different sorts of situations, and it's not fair for students that do have to come down and get their stuff to have to be on the same schedule as people who don't. And I totally understand that.
Oh, thank you.
Yeah, and then if there's anything that I mean, here's how I look at it. If there's anything that's impacting your education in any shape, way, or form that I can help with, just let me know because everyone's under a different set of circumstances. I mean, it's just we've never had to deal with this before, so we have to be really, really flexible. What other questions or problems do we have? And by the way, I'll say really quick, Norman, I'm really glad you brought that up because these are things that I won't know unless you guys communicate it to me. So again, any sort of needs you have, just feel free to let me know.
I wasn't really. I'm planning on doing the quiz today. I think that's the due date. But what's the formatting like? I'm still kind of confused on that from the messages. I was just wondering what it would look like.
When you say formatting, what do you mean exactly? Just so I understand.
Is it like the homework we've done, or what does it look like?
The quizzes are on my math lab, and so
Okay.
they'll
Yeah,
be
I
like,
know that. I just mean like I don't know. Are you solving? Are you just saying like it converges, it diverges, or are you like, well, what's it? What are we going for?
right. And the best thing to do is when you take it, it will be relatively self-explanatory. But
Okay.
but when you're dealing with series, like we were saying last time, there aren't that many series that you know what they actually converge to. Okay, and
Okay.
the only ones that you know are geometric, telescoping, and P series. We know actually you guys don't know formally what the sum of 1 over n squared goes to because I have.
So you're basically just saying it converges or it diverges.
For the most part, that's actually the main
Okay.
the main question we have. Yeah, exactly. So
Okay. Yeah, because I know on the problems we've been doing in the past, I guess week we've been doing these. It's just been like that. So. Okay.
yeah, and that's what makes it different than integrals. I mean, there are techniques for figuring out what it converges to, but that requires you just do more math. The only way it'll be different is that you'll have to show your work.
Mm-hmm.
And again, I think Turnitin's not working for a lot of people, so I just suggest take pictures on your phone.
Did you put the class code up? I still need to join actually.
I'm sorry?
You put the class code up, right? It's on the announcements.
Class code.
Return. Oh, did you do it within Canvas?
Yeah.
Or how did you do it? Oh, okay. I'm just thinking back in high school, we had to join a class, and it was through a website and everything. So I was just a little confused.
For Turnitin or for my math lab?
For Turnitin.
Huh.
Yeah.
You should be able to do it through Canvas.
Yeah, no, I have in my humanities. I was just thinking back to high school. I don't know. It was funny.
You know what? And I don't know either. We're both figuring this out. So
yeah.
Worst comes to worst. I mean, here's how I look at it. Just really simply is let's just keep things simple.
Mm-hmm.
I don't want people to have to download special software and all this stuff and have to deal with it.
Yeah.
If you just want to take pictures, I think that's not so bad really. You can take pictures, go to an email.
I know if you have an iPhone with the Notes app, you can scan it and turn it into a PDF to paper.
There you go. Yeah. So whatever works, whatever's easiest. You know me. I'm not for complicated, especially not now. Okay. What other
Thank you.
questions? Sure, absolutely. What other questions do we have? Okay. The video for the comparison test is that should be that's a good question. I don't think I posted the video for the comparison test, and I'll tell you why. Because it's not technically required. I do have the notes for the comparison test up, don't I? I'm pretty sure about that. So Daniel's asking about the comparison test. Although I don't think I have the video up because I didn't make one. I do know that. And like I said, the reason why I didn't do that was because technically it isn't required. But I should have, let me just check to make sure I'm not a liar here. I should have the handwritten notes. Give me 1 second. Sometimes when a lot of apps are going, the phone kind of slows down a little bit. Yeah, so right here. So Daniel, if you go to Monday 3/23, you'll see a comparison test, and it should download some handwritten notes here. Okay. Alrighty. And it is in the book. It's section 10.4, I believe. Okay. Yeah. And so here's the thing. I'm going to actually go through the comparison test today. So if you have any questions, I'll kind of cover that. All right. Okay. Excellent.
For the homework, can we go over one of the questions for the infinite series?
Sure.
Or what was that?
Sure.
Okay. That was I posted the picture in the chat. I got most of it right, but for the last one where the convergence, when you solve it, I kept getting different numbers.
Okay, let me catch up with you here for a second. Okay. Okay, so the one that was throwing you off was this one. What does it converge to?
Yeah.
Okay, so this is a geometric series, and it's a little tricky because of this term where you have alternating signs on this last term. Okay.
Mm-hmm.
So let me we'll just kind of work it through here. So n starts at 0, which is good because that's where the geometric series starts, right? And then it's 3/2 to the nth plus -1 to the nth over 3 to the nth. This is a kind of common sort of problem, okay? So first thing to do is to split these two guys apart. Okay, so this is my total series S. I'm going to split this apart into S1. And I actually know what S1 is because this is just a straight geometric series. This has the form n equal to 0 to infinity of a times r to the nth. And I know this converges to a over 1 minus r when the absolute value of r is less than 1. And I can use that formula because in this case my r is 1/2, right? So if I just quickly rewrite this, you can see that I get this, right? So I'll have 1 minus 1/2, which will be 1/2 on the bottom. It'll flip, and that'll give me a 6 when I multiply by the 3. Okay?
Mm-hmm.
Now, the other one's the hard one, okay? And I guarantee you there'll probably be a problem like this on the exam. What makes this other one hard, and we did a problem like this, I think, well, I know we did a problem like this before the break. So kind of the trick here is you want to write out the first couple of terms, Okay, so let's write out the first couple of terms. So when n is equal to 0, this is 1, right? Then this is minus 1/3 when n is equal to 1. Okay? When n is equal to 2, minus 1/2 squared is positive 1. 1/3 squared is 9. And so on. Minus 1/27 plus 1/81. And what I'm going to do, and kind of the trick here, is to realize I have two geometric series. When you have something like this, when you have minus 1 to the nth times another quantity to the nth, you actually have two geometric series. And the way that you kind of figure this out, you puzzle through all this, is you group the positive terms and you group the negative terms. So if I look at the positive terms, I get 1 plus 1/9 plus 1/81 plus ... right? If I look at the negative terms, I get minus 1/3 minus 1/27 minus 1/243 ... right?
Yeah.
Now, you can take my word for it, or you don't have to. You can convince yourself, okay? But this is a geometric series. And if this is a geometric series, the way that we understand a geometric series, it always starts with 1 plus r squared. So r must be 1/9, right? Okay?
I'm kind of lost at that part.
Okay, so what is a geometric series? Well, geometric series is where you're adding powers of r, right? So this first term is r to the 0 plus r to the first plus r to the squared plus ...
Oh, okay. That's the series. Okay, that makes sense.
Right. So now we know what our r is. R must be 1/9. So this guy converges to 1/1 minus r, because if r is 1/9, absolute value of r is less than 1. Plug all this in. 1 minus 1/9 is 8/9. Flip it. It's 9/8. So that's our value for the positive portion of this one sum, okay? Now I play the same game here. I want this first term to be positive 1 also, right? So if I factor out a minus 1/3, whoops, notice I get exactly the same guy that I had here. Minus 1/3, this becomes plus 1/9 plus 1/81 plus ... Okay? Well, this is the same series I just did a second ago, right? This guy right here. These are identical. So this just becomes minus 1/3 times 9/8. Isn't that cool?
Yeah.
Now, what some people do, and you can do this if you want, some people just remember the formula. The formula, and I hate memorizing formulas, and I hate for you to do it too, but the formula for this, we can kind of see what this is now, right? This is 1 minus, actually, I'd be a little careful. And you know what, let me not do this, because it's going to be, it's going to be a little messy. It's basically 1 minus the square root of r over 1 minus r, but that's okay. So this is all we need. So now we can put it all together, right? So S is equal to S1 plus S2. S1 was 6. This guy, when I kind of break this down a little bit, right, I can factor out a 9/8 and I'll get a 2/3. Get a little cancellation going on there. Plus 3/4. And that's it. So you get 27/4.
Okay, that makes sense.
And that's what. Oh, okay, that's the right answer. Okay. Now, I'll tell you one thing really quick. You can check yourself online. I mean, one of the reasons why you have to show your work is that there are online solvers. So if you type in like online infinite series solvers, you'll find them. And I won't. Wolfram has it. There's a gazillion. You can pick the one that you like best. Okay.
All right.
All right. Good question.
Thank you.
Other homework questions, because these are kind of like bedrock to what we're going to do today. Okay. Okay, so what I'm going to do is I'm going to pick up where I left off last time. We're going through those 14 problems. So remember, we're working these 14 problems that are in the root ratio notes. Okay, and we got through the first 7 last time. So I'm just going to pick up from there, okay? So number 8 was, let's see, 2, 3, 4, 5, 6, was H. And in H, we want to look at the convergence of the following series. And like Joseph was saying a second ago, we're really primarily interested in convergence. If they ask you what it converges to, you know that it has to be one of our known nice series, okay? So here I just want to tell if it converges. Okay, so what should I do with this infinite series? Who wants to kind of make a guess?
We would break it apart.
Break it apart. Whenever you can do that, break it apart. So first we're going to try to break it apart. And the logic behind this is, if when I break this apart, so notice with Nissan's problem, I just did that a second ago, right? I broke this into 2 parts. If I can break the sum into 2 other infinite series and both of these converge, then I know that this converges also. Okay. If on the other hand, one of these diverges, then this diverges also. Okay. So let's see. N equal to 1 to infinity. Okay. Now we have to look at each of these infinite series by themselves. The first thing I'm going to do is I'm generally going to try. Sorry, it's hard to put this in the center of the screen. First thing I should always do is I should test for non-convergence. In other words, what I'm hoping that when I take the limit of the terms in the sequence that I'm adding up, I'm hoping that they won't converge to 0. And if they don't, then my problem's done. Right? I know my infinite series does not converge. Notice that in both of these cases, they're going to converge, right? I have a number greater than 1, raising it to the nth power. As n goes to infinity, that goes to 0. So both of these tests, both of these infinite series, I can't apply the test for non-convergence, okay? So this doesn't help us. You could say this is indeterminate. It doesn't tell us at this stage. Okay. Does everyone see why that's indeterminate? Does everyone see why these go to 0? We're looking at these terms right here, right? Okay. I'm gonna take the silence for everything's okay. All right. So now we're ready. So we look at this. The first thing we always do, again, what we always do in these problems is we try to pick the low-hanging fruit. We try the simplest things. So the next thing we do is we see if our series is a series whose convergence we know about. And what I mean by that is, if you go back to the handout, let me show you the handout really quickly. Give me 1 second. Let me just do this. Where is it? Well, if you go back to the handout, I can't find it right off the top of my head. If you go back to the handout that I posted, I basically gave the infinite series whose convergence we know. And we only know a few, right? We know telescoping. And telescoping is very rare, okay? We know about telescoping. We know geometric series. And we know p-series. We actually do know about the convergence of these three series. Do either of these infinite series fit into one of these categories?
I think S1 looks like a geometric.
Yeah, if I call this S1, this is definitely geometric. And I know this converges because here, so this is clearly a geometric. And my R, which is equal to 1 over 1.25, is definitely less than 1. So I know already that this converges. All right. Now, how do we deal with this one here? Technically, this is not. Well, technically, this actually is a geometric series, right? Because I can write this as. Okay. Everybody agrees? So this is minus 1 over 1.25 raised to the nth power, right? So this is also a geometric series. And remember that the geometric series really, when we're doing this test to see when it converges, it really applies to the absolute value of R. I didn't bother to do it here because obviously I'm looking at positive terms. But here when I have negative terms, the same observation applies, right? That this guy, the absolute value of R here, is less than 1. So both of these converge. The sum of two convergence series converges. Okay? Another way that you could do this, and I'll mention this because suppose, for example, you didn't see this right away. Remember one of the other tricks I told you? I said, look at the absolute value. Okay, so look at the series where we're working with the absolute values. And if this converges, your original series converges. And if you took the absolute value, you would just get 1 over 1.25 to the nth power, right? Clearly a geometric series, clearly converges. So if this converges, your original series converges also. Okay? So there's a lot of different ways to look at these problems. All right. So we're done there. So they were both geometric. Questions that we have on that? Okay. One of the things that will help you when you're preparing for an exam is to kind of outline your thinking, is to kind of think at each stage, what am I doing? What should I do next? Okay. So again, low-hanging fruit. If the low-hanging fruit doesn't work, then you have to use an actual test. And the next is one of these problems where I have to do a test. So problem I, I'm looking at the series from n equals 0 to infinity, e to the minus nth times n cubed. Now, a lot of times when you're working with these problems, it helps to kind of geometrically, it helps to algebraically re-express these. How could I rewrite this infinite series in such a way that I'm kind of doing a little bit of algebraic manipulation that might help me?
You'd put the e raised to the negative n on the bottom.
Exactly. You don't have to do this, but this will make your life a little easier. Okay, good. All right. Now I'm going to go through my 3 stages, okay? Step 1, I'm going to test for non-convergence. If you guys don't mind, I'm just going to use NC for non-convergence, okay? So I'm going to ask, does the limit as n goes to infinity of n cubed over e to the n equals 0, not equal to 0? Okay. So what is the limit of n cubed over e to the n as n goes to infinity? Anyone want to take a guess? Okay. Oh, did I hear someone stirring?
0.
It is. It's so why? You said that in a kind of questioning voice. Why?
Because one is a smaller infinity divided by a larger infinity.
And so you're on the right track. And so the question is like smaller how? So we have these rules for how functions grow asymptotically. And let me kind of
E to the n's climb is much steeper than n cubed.
exactly. So these are the hierarchy of how things grow asymptotically. So this is talking about this says this is asymptotically less than this. This isn't a symbol in math. This is just something I made up. This looks like kind of like an infinity sign and a less than sign. Okay, I just made this up. There actually is a notation, but I don't want to make things complicated. What this means is that if I look at the natural log of n divided by n to the alpha, for any positive value to alpha, this limit goes to 0 as n goes to infinity. That's what it means. So what this says is that natural logs they grow less asymptotically than power functions, which grow less asymptotically than exponentials, which grow less asymptotically than factorials. Okay. And so this is clearly a case where I have a power function over an exponential function, so the limit's going to be 0. So here it does not apply. It's indeterminate. I know that this limit is actually equal to 0. So the test doesn't tell us what happens when it's equal to 0. It only tells us what happens when it's not equal to 0. So that doesn't help us. Shucks. Step 2 is this and here's what I'm going to kind of do, and I'd like you to make this sort of analogy in your mind. That second step where we talk about, like, does this correspond to a known series whose convergence we know something about? You could think of these as kind of like summation formulas, okay? In the same way that you had integral formulas. So we could ask, is our series, one that we, have a formula for? In other words, we know it's convergence, right? It's a known quantity. Well, you look at this and it doesn't correspond to anything that we know, right? It's not a telescoping series. I can't split this apart as the difference of two different sequences. It's not a geometric series, okay? And it's not going to be a P series. So now we have to go on and actually apply a test for convergence. So the answer here is no. So now we have to apply one of our convergence tests. And we have a couple, right? We have an integral test, we have a comparison test, a root test, and a ratio test. And here's what we're working with. Which do you think we should try? And this is kind of up in the air. I'll be honest. When I was a student, half the time I just guessed. Okay, and if it works, great. If it doesn't, you try another one, right? So which one would you guess that we try?
The ratio test, since it's already in that form.
A ratio test is a good guess. That's probably what I would guess when I was a student. So the ratio test says we want to look at the limit. What's going on here? Limit as n goes to infinity. And I want you to write out what we should write here. I want you to write it out first. See if you can figure out what I should put here. Okay, so why doesn't someone tell me in words what it is that I'm doing? What am I doing in words?
I don't know how to do any of these tests yet, so I can't help.
Okay, so here's what we're doing. We're looking at the ratio of consecutive terms in the series. Okay. And we want to evaluate this limit. Okay, so if I put in n plus 1, try to adjust this a little bit. There we go. So if I put in n plus 1, the nth plus 1 term is what? Well, it's I just put in n plus 1 for n, right? Okay. And of course, a to the nth is just the original series terms, right? And then I'm just going to flip this guy and multiply him, right? So I'll get n plus 1 over n cubed times e to the nth over e to the n plus 1. Okay.
Is the ratio test the same method that you used to find the R value?
No, the R comes out so the R comes out naturally. So the R comes out when we have an infinite series whose AN has a specific form, right? So the AN has to have a form that looks like this. Okay, R to the nth.
Oh, okay.
That's when we get R, right? Okay, so this is actually rho. This ratio is rho, which is the Greek letter for R. And there's a reason why. There's actually a relationship between geometric series and ratio, but we won't worry about it right now. Okay, so now I evaluate this limit as n goes to infinity. I can actually break these two limits apart, right? So the limit as n goes to infinity of n plus 1 cubed over n cubed times the limit of, and what does this guy become right here?
One over e.
1 over e, piece of cake. And of course, that's just a constant, limit, so we don't care about that, right? This guy converges to 1, right? Hold on a second. Whoops. Yeah, that guy converges to 1. I'd be a little careful. Yeah, this guy converges to 1. If I went ahead and I expanded this out, I'd have an n cubed on top as my leading term, have an n cubed on the bottom. They'd cancel, right? So this becomes 1 over e. That's my rho, and that's less than 1. So the ratio test tells me that this converges. And if you go back, Daniel, if you go back to the handout on the ratio test, you'll see that I actually kind of give the conditions. So if you want to download that will help a lot. Okay, let's make sure I answered your.
I'm watching the video.
Yeah, I think the notes will help a little bit more. If you just download the notes, I think you can follow and it'll make a little more sense. Now, there are other ways of doing this, okay? You could try the root test. The root test is going to be a little hard, though, because here's what you have to do. I have to write this as 1 over nth to the nth cubed. Okay? And then this will be n to the 3 over n to the nth over e to the nth. And when I take the root, the same sort of thing will happen. Okay, I'll find out that I get 1 here, but there's a little more manipulation. You have to write n as n to the 1 over n raised to the nth power. Okay, so I think the root test here is a little harder. I think this is easiest, harder. You could actually do this using the integral test, and you'd have to use integration by parts. So this is a capital H for very hard. Okay. All right. All right. I'll show you a really quick little trick that you can use though. So this is a trick. You guys will learn this eventually. But the integral from 0 to n of x to the n times e to the minus x dx is n factorial. Okay. this is actually a very useful result, and you'll learn this later on in your math. And you can see why that happens, because every time you do integration by parts, what happens is you bring down another exponent, right, of n, and that ends up giving you the n factorial. So if you know that formula, you can actually use the integral test. So this is something known as the gamma function in mathematics. So if you want to do something kind of fun, this is kind of a fun little thing to explore. Okay. So any questions on that? Okay. So we made a good guess. It worked out well. We won't always guess well, but that's okay. All right, let's look at J. J is a harder problem. Whenever you start to get natural logs, things can get a little harder. Okay. And I want to try to look at the convergence of this infinite series. All right. Which way do you guess might be the easiest? Integral test is out, right? Ratio test, we can try it really quick. So a lot of times you kind of do a little pre-test, right? So the ratio test would look like n plus 1 over n times the natural log of n plus 1 raised to the n plus 1 divided by 2 over natural log of n raised to the n plus 2. Okay, this is looking a little hard to me. Okay, so I'm probably not going to pursue this because it's not so obvious how to deal with this limit. Okay. So what I might try is the root test. So I'm going to say this kind of looks hard. I have to evaluate this limit. This guy will be easy. This guy not so easy. So whenever you have natural logs, it kind of messes things up, right? Let's try the root test. So what I want with the root test is I want something raised to the nth power, right? I don't have that. The bottom I have raised to the nth power, but the top isn't. So I'm going to have to do a little bit of manipulation, okay? So this is what I want, right? So what I'm going to do is I'm going to re-express n in the numerator as n raised to the 1 over nth power raised to the nth power. Okay? And then I'm going to have natural log n of n to the 1/2, which is natural log square root raised to the nth power. Okay, so there's a little bit, well, I'm sorry, natural log of n, sorry, raised to the 1/2 power. Okay. Is everybody good on seeing this first of all before we go any further? Everyone's good?
Could you write out the a of n form of like the root method, how you did for the ratio back in problem I?
I'm sorry. Okay, you mean here?
Is that it?
Well,
The one where you showed us how to apply it to any general series?
Okay, so say that again. I want to make sure I understand.
So when you showed us the ratio test in problem I, you did lim of n goes to infinity is equivalent to a of n plus 1 divided by a of n.
Yeah, right.
Is there something similar for root?
No, the root test tells you, so for the root test, that's a good question. So for the root test, what I'm looking at is a different quantity. I'm looking at the limit as n goes to infinity of the nth root of the series terms that I'm summing up. Okay, this is what I'm looking at. This is my row here. So let me just show you really quick what it is I'm talking about, because this is really confusing if you're kind of not on the same page here. Let me go back just 1 second really quick and show you this one thing. Let's see. Give me 1 second. Comparison test note. What did I do with that? Yeah, here it is. All right. So this is the overview that I did. And this is talking about the different tests. Okay. So for the ratio test, I'm looking at the limit of the ratio of successive terms in the series. For the root test, I'm looking at the nth root of the terms in the series. Okay. And the cool thing is that the limits of both of these, I use the same decision rule to determine convergence. Even though I'm looking at the limit of different things, this quantity rho, I apply exactly the same test to. All right? Does that answer your question?
Yeah.
Okay, good. Okay, so now we got a little bit of work ahead of us, right? So everyone's good on this, on how I wrote this right here? I'm basically just breaking this apart, right? So now I could go ahead. So this is, now I've written a to the nth as, let me expand this a little bit. Okay, I've written this as n to the 1 over n over the square root of the natural log of n raised to the nth power. And now I can use the ratio test. I'm the root test, or I can try. Okay. Get this centered here for a second. Okay, here we go. So let's go ahead and try it now. So the limit as n goes to infinity of the nth root of the series terms I'm adding up will be equal to the limit as n goes to infinity of n to the 1 nth over the square root of natural log of n raised to the nth power, and I'm taking the nth root of that. And of course, I cold-bloodedly set that up because I know that the nth power and the nth root are going to cancel, right? And that's going to leave me with the limit as n goes to infinity of n to the 1 over n times the square root of natural log of n. Okay? And this is actually not so hard to evaluate because we're going to use this fact that we talked about yesterday. So there's a really useful fact to use here. I'll show you this fact. There are actually two useful facts. The first says that the limit as n goes to infinity of the nth root of a number is equal to 1 if it's positive. But the more interesting result, and this first fact, by the way, if you played around a little bit on a computer, you can convince yourself this is true. This is actually not so difficult to convince yourself of. This is a little harder though to see this. And this is the fact that I want to use here. Now, some of you probably are going, what the heck, right? All these facts. Here's the thing. You want to make a list of these facts. So the asymptotic growth, that's an important fact. This formula, important fact. Okay? So if I use this, I can split. I realize that this is going to converge to 1. This is going to converge to infinity, right? 1 over infinity is going to converge to 0, right? So this thing is equal to 0. And again, if I go back to what the statement of that root test tells me, this is my rho. It's less than 1, right? So this limit is equal to rho. It's less than 1. Therefore, by the root test, my series converges. Okay. So how is that looking, guys? Is that making sense, or does that seem a little strange?
Yeah, that looks good to me.
Okay, so let me just kind of
I found
yeah.
process, but not the algebraic manipulation of the original function.
I'm sorry, what's that?
How you transformed it from n divided by ln of n to the n divided by 2.
Right.
I don't realize how you transform it.
Okay, so all I did here, so here's kind of something to think about. When you're going to apply the root test, this is what you want. You want the entire summand. You want to write an as some quantity all raised to the nth power. So I'm going to take the nth root, right? So this part in the bottom is already done, okay? But I can realize that I can write n to the first this way. Why? Because I can write 1 as 1 over n times n, right?
Yeah.
And I know that when you multiply exponents, it's the same as raising that quantity to that power, right?
Yeah.
And that's all I'm doing.
So anytime you take the root test, you put a of n and raise it to the nth power.
You sure try. That's what you
try.
try to do. And again, sometimes it'll work, sometimes it won't. And you say, oh crap, I should have used the ratio test or another test. Okay. Now there's another way. Now there's another way of doing this problem. Okay. And this is something to think about. Okay. Whenever you have natural logs, it's a good idea to consider using the comparison test. Okay. So one of the things that we know is that the natural log of n is less than n. All right, and sometimes it's useful to we actually know it's less than n, but asymptotically it's also less than n to the alpha. So sometimes it's useful to make this replacement and replace it by n. In this case, it won't work out, and the reason why it won't work out. And if it doesn't make sense to you, that's okay. Sometimes we're going to use this fact. Now, the reason why it won't work out in this case is because when I take the reciprocals, this becomes greater. Okay? And what I need to use the comparison test is I need this to be less than this, and then I need whatever this series was involved in to converge. So here this won't work out, but this is often a very useful substitution along with a comparison test. And when I'm doing this series myself, I usually think of this first, because if I can use this, it will help me a lot. Okay. All right. Okay. But we're done. The root test works just fine. All right. Shall we go on? Hey, let me ask you guys a question, because I'm just out here talking, okay, and since I can't see people's faces, I don't know if everyone's following or bored, or they're clueless and their head's spinning. Where are people at? Do you feel okay with what I'm telling you? Does it make sense when I say it, or do you feel like you're really just kind of weak on the fundamentals of how to even set it up? I need some feedback here, guys.
So with the current stuff, I feel pretty good. With the farther back things, like the telescoping and geometric, where we did it in the YouTube videos, that I feel a little more murky.
Can you say that again, because you kind of broke up? I'm sorry.
Sorry, I don't have headphones with my computer. My wired ones are at school.
That's okay.
I'm back home, but I'm feeling good on the root tests and ratio tests, but like I'm still the telescoping and geometric stuff where we did those in the YouTube videos. I'm still a little murky on that.
Okay, so two responses. First is telescoping you're rarely going to see. Okay.
Okay.
Telescoping is a very special case, and usually you can see it coming a mile away. But telescoping, I'm not going to really deal with telescoping. Geometric series are really important.
Okay.
And so Nissan, I think, kind of asked a question about geometric series too. If it would help, one of the things I can do is I can post like a Khan Academy on a geometric series.
Okay. Yeah, that would be good. Thank you.
And I think, and one of the reasons I like Khan Academy, even though they're not a substitute for class, they kind of cover the basics. The guy does a really good job of just hitting the basics so that you kind of know what's going on. So I'll go ahead and post those. Okay, that might help a little
Cool.
bit.
Thank you.
I don't know if more problem solving sessions would help. I'm totally up to that. One of the things I'm more than happy to do is kind of set up a problem solving session where I can work at an actual board. One of the things that's not ideal about working on my tablet is if I lay my tablet flat, I have a Surface Pro and the fan has a hard time sucking in air. And so you'll hear the fan because it's working overtime, okay? Which isn't good for my computer anyhow. So I have to work with it kind of propped up. And of course, me writing on a propped up, me writing on a flat surface is bad enough, right? But on a tilted surface, I'm just deadly, So it's kind of hard to read a little bit. So I'd be more than happy to do like a problem solving session if you guys want to do that. What other sort of feedback? Heidi?
I'm on the
Luke?
opposite spectrum where I'm really comfortable with geometric and telescoping, but because I haven't gotten to cover root ratio and comparison, I don't know how to do that. But I will catch up on that on my own time.
Okay, yeah, and I know everyone's at a different stage right now because we're all going through different stuff. So, yeah, and that's why I mentioned, I don't know, Daniel, if you heard me talking to Norman in the beginning, I said, if you guys need extensions on anything, feel perfectly free. I could care less when you learn it. It's of no consequence to me, as long as you learn it. And, it's, especially since we're not in a classroom environment, it's going to take people longer, not just because of the fact that they're dealing with stuff, but also because of the fact that it's more challenging for some people to learn remotely,
Yeah.
Other feedback. And by the way, Heidi, to answer your question, I missed your question earlier. I am recording this one. I think most of the sessions we've done, I have made recordings, and I'll post the recording afterwards, okay?
I do have one more question.
Yeah, sure.
It's really nice note called Overview, but I couldn't find a copy of it to print out. Like it's in videos that you used it on, but I couldn't find a blank copy to print out.
Okay, a note to self. I'll post that right afterwards because that overview actually is really useful. Sorry about that.
No problem. And a video for you filling it out, I didn't watch that one.
I'm sorry, can you repeat the last part? You kind of cut out a little bit.
If you have a video that with filling it out.
Let me see about that. I'm not 100% sure. Let me kind of see about that. Yeah.
I think there might be because I think I found it, but I'll check again.
Okay, I do have the handout for the overview, the shell of it, so I will post that. And if you need any other videos, I'll look around. I try to do them all every once in a while. I think the only one I haven't done is the comparison, and like I said, I didn't do that one because it wasn't required. Okay, so okay, shall we move on?
Yep.
Okay. And by the way, let me just say this, okay, just really quickly, but this is, I don't want to beat a dead horse, but this is important. If there's anything that would kind of like, here's something that would kind of help you. If when I say something, you just say like, I don't get that, or I don't understand that, even if it's because you're not up to date, that's perfectly fine. I would rather you do that because then I can point you in the right direction at least. I mean, we may not be able to like remedy it right now, but at least I can kind of point you in the right direction, okay? Okay, so the next infinite series is this infinite series right here. And I'll make one last comment, which is whatever I tell you in lecture is fair game. This is fair game in lecture. So I'm going to tell you a lot of things that the book doesn't tell you, but they're perfectly fair game. You can use them, okay? All right. So we look at this. First of all, we try the test for non-convergence, right? Does it tell us anything? No.
That it possibly could converge.
Exactly. That's why it's indeterminate, right? The test only tells us what happens when this is not equal to 0. But in this case, when I take the limit of the series terms I'm adding up, it gives me 0. So it doesn't tell me anything about what happens when this is 0. You're right. May converge, may not converge. So it's indeterminate, right? Shucks. We could have been done with the problem, right? Okay. Does this converge to any of our known series? Or is this any one of our known series? Okay, this is tricky. So notice something, that this actually is kind of one of our known series. It's a combination of two P series, right? So in other words, I do know about the convergence of this series, right? I know that this converges when the power P is greater than 1, and I know that it diverges when P is less than or equal to 1, okay? I don't have the P series exactly. I have two P series. Does anyone want to take a guess as to what I could do here? How I can use this result for here? When I have two series and I have a situation like this, what do I consider doing?
Is it S equals S1 plus S2?
Right. The smart thing to do is to break them apart. So if I break my entire series apart, just like you said, I'm going to break this up into two sub-series, if you want to call it that, I guess. All right. I do know about the convergence of these two, right? And here's something to realize, okay? If something converges, I can do stuff like this, okay? I can split these things apart like this, all right? This guy converges. This guy diverges, right? We go back to the rules for the P series, right? When P is less than or equal to 1, it diverges. What do you think I can say about the whole series then?
It diverges.
It's going to diverge. So whenever you split a series apart like this, okay, if both of these converge, the original series converges. But if either one of these diverges, this diverges. Okay. So I know already that this diverges. There actually is a way I could prove this. Suppose you say, I don't believe you, or you say, oh, you know, I don't want to remember these rules. That's fine. There is another way we can prove this. Notice I could use the integral test. Okay. So the integral test says the following. It says take your series and substitute x for n, right? From 1 to infinity. That's what the integral test says. It says replace the summation by an integral, keep the limits of integration the same as the limits of the summation, and change n to x. Isn't that cool? All right. If you try to evaluate this integral, what are you going to find?
Is it like ln of x minus?
Right.
Yes.
So what you're going to find when you evaluate this, notice that this is an improper integral. So technically I have to evaluate this like this, right? This is the limit as t goes to positive infinity of 1 to t x to the minus 1 minus x to the minus 2 dx. And you can see what's going to happen, right? Whoops. And Daniel kind of let the cat out of the bag, right? This is going to be natural log of t minus natural log of 1 minus, scoot over here. And when I integrate, right, this is going to become minus, and then this will become positive 1 over x, right? And it'll be positive 1 over t over positive minus 1 over 1.
One of them is an error, so it won't exist.
One of them, when you say it's an error, what do you mean? I'm not sure I follow.
Limit of 1, or ln of 1.
Well, the ln of 1 will go to 0, right? That's easy.
Infinity then. My bad, I don't know.
But you're absolutely right. The ln of t is what's causing the problem. So the limit as t goes to infinity of this goes to infinity. So the integral test says, the integral test is really cool. It actually works both ways. It says whatever this integral does, well, here's what it says. Whatever one of them does, the other one does. So if this converges, this converges. If this converges, this converges. If this diverges, this diverges. If this diverges, this diverges. It goes both ways. Whatever one does, the other one does. So this one diverges, so this one diverges. Okay. So there's more than one way to deal with these sorts of problems. All right. Okay. Everybody good on that? Okay. Does that shaking of the screen bother people? Is that too noticeable?
I didn't even notice the shaking.
Oh, good, because probably the frame rate is actually really low, so the refresh rate, because of the fan, it jiggles a little bit, but because of the refresh rate, you guys probably don't even notice that. Isn't that cool? Okay, so problem L. Before I move on, though, is everybody good on this? So there's two different ways to do it. The one is you can split it apart, and we're going to use this fact that if one of the subseries diverges, then the whole thing has to diverge, okay? But you can use the integral test too. Okay. All right. So, do you guys want to try to practice setting this up?
We can give it a go.
Yeah.
Okay. So what I want you to do is apply the test for non-convergence. Always do that first. I mean, you might get lucky. Then you don't do the darn problem, right? That's going to save you a hell of a lot of headache. Okay? See if it's any one of our known series. And then if it isn't, figure out which test you're going to use and try to set that up, okay? And if you don't mind, I'm gonna run to the restroom really quick, okay? While you guys are doing that. I'll be right back.
Did you guys get infinity divided by during the non-convergence test?
Yes.
And that's 1, if I'm thinking right?
I don't know, because the exponential grows to infinity faster than the
Yeah, true. So it would be infinity then?
I think it would be infinity.
Okay.
Yeah, it goes up to infinity, so then the
Doesn't
series.
converge. Right?
Okay. Are we making some progress here?
Yeah, we kind of, I think we all agree that it doesn't pass the test for non-convergence.
Right, because I have an exponential function over a power function, so I know that limit's going to go to 0, so it doesn't do it. It doesn't correspond to any known series, right? I mean, you have something that kind of looks like a geometric, and this is not even a P series, so we can't do anything with that. So no. So the real question is, what sort of test are we going to run here?
Oh, we all thought that it equaled infinity, actually.
Interesting. Okay.
I think, unless I'm misstating.
Yeah, no, that's what I thought.
I actually, hold on. Let me back up. This is not 0, right?
Yeah.
It's infinity.
Exponential.
Yeah, it's infinity. So this does pass the test for non-convergence, meaning that we know already that this thing does not converge. Okay.
I guess I said it backwards, but yeah, that's what I meant when I said that.
Yeah, and I wrote this. I should have done better. Right. An exponential overpower exponential wins does not converge to 0. It converges to infinity. So this thing does not converge. So we're done. No more work. That's why you always use that test first, okay? All right, great. Okay. M. Okay, this one's a little complicated. Okay, so let me make a comment. Test for non-convergence, you use it when it's easy, okay? You can actually use it here, okay? We can use a test for non-convergence. But here's the thing you want to understand is that the test for non-convergence is kind of like leading terms, okay? So when you're doing this, and so here's kind of just one way of looking at this. If you try to test for non-convergence and it's hard for you to do, don't do it. Okay, it's really meant for when it's an easy problem to look at and analyze. When you're doing the test for non-convergence on something like this, you still use the leading term, just like we did with any sort of limit at infinity, right? So the leading term in the numerator is n2 to the nth, right? The leading term in the denominator is 3n. Okay?
Yeah.
And
would it be 4 times n or
Oh yeah. I mean, technically, there is a two here out in front. Okay, and I don't really care about that. I'm more interested in what's going on the function part. But yeah, there should be a two times n times 2 to the n. Yeah, you're absolutely right.
Okay.
But what I'm looking for is if this converges to 0, so the 2 won't affect it too much, right? Okay.
Yeah.
So I go ahead. I can pull the 2 out if I want to. I'm going to have n times 2/3 to the nth. Okay. And I'm going to write this now as a ratio. Why? Because I want to look at how things grow asymptotically, right? Okay. So when this a is greater than 1, and I should make a comment. Let me make one comment here really quick, because what I wrote here earlier is not 100% correct. I don't want to tell you something wrong. This is true when a is greater than 1. Okay. The base has to be greater than 1. So here, when I apply the test for non-convergence, I have a power function over an exponential where the base is greater than 1. So this thing converges to 0. Okay. So when you use a test for non-convergence and you have a ratio, you can use the leading terms. But this is a problem that actually I think wouldn't be easy for most students to see that necessarily. So when the non-convergence test is not so easy for you to apply, just skip it, okay? And if you and the only reason you'd come back to it is if you keep trying all the other tests and you can never show that it converges, then you might say, you know what, maybe it doesn't converge. Maybe I need to go back and do the work necessary to do this carefully, okay? But here it's a little hard to apply. Does it correspond to a known series? Absolutely not. I mean, this thing is an absolute mess, right? It's really complicated. It doesn't look like anything we've worked on. So the answer to that is clearly no. Okay, let's think about the test we want here, okay? So you look at this thing, this is pretty complicated, right? And this is 2 to the nth plus 3 over 3n plus 1. Okay. So here's what I'm going to do, okay? Is I'm going to split this apart, and I'm going to go ahead, I'm going to consider multiplying all these guys, okay? And what I'm going to do is I'm just going to look at the leading term and the numerator. So here's what I want to say. If I went ahead and expanded this out, I would get 4 terms, right? Everybody agree?
Yeah.
Okay. All I'm going to do is I'm going to look at the term that has the largest numerator. If I show that converges, I show all of the others converge by the comparison test, right?
Okay.
So in other words, here's kind of the idea. Let me just expand this out. So if I go ahead and expand this out, I get 2 times n, the 2 to the nth, plus 3 times 2 to the nth, plus 6n plus 9 over 3 to the nth plus 1. I can split this apart into 4 sub-series, okay? Notice that every term, if we kind of think about what the comparison test says, okay, I'll just write this out really quick. Oops, plus 1, plus 3, plus 6, plus that's an absolute mess, okay? So what I'm going to do is I'm going to use the fact that if I think about all these series, this series, its terms are always larger than all of these other terms. If you look at this, right, 2n times 2 to the nth is greater than each of these terms, okay? So if I can show that this converges, by the comparison test, I automatically know all the rest of these converge. All right? Does that make sense? So what
Yeah.
what I'm going to note here is that the series terms are the largest of all these series. So if this converges, the other ones have to converge, okay? Now, you don't have to do it this way, okay? You can evaluate each of them separately and try to show that each of these converges, okay? But this is kind of the faster way of thinking about these things. Now, this is a perfect example of where we want to use the comparison test. What I'm going to do here is I'm not going to work with this series. Oops, sorry. It's hard to center this thing sometimes because it gets lagged down by the video. Okay, what I'm going to do is I am going to use the comparison test here, and what I'm going to do is I'm going to replace this by 3n. 3 to the nth. And the reason why is I'm going to notice that 1 over 3 to the nth plus 2 is less than 1 over 3 to the nth. Okay? So I'm going to make this a simpler series. And what's going to happen is this series is going to be bounded above by this series. This is what the comparison test does. It takes a series that has positive terms, it bounds it above by another series that converges, and therefore the series that has the smaller terms also has to converge. So here's what I'm going to do. Here's how I'm going to start off. First, I'm going to use the comparison test.
I have a question.
Sure.
If the series that you bounded above by, like 1 over 3n, if that doesn't converge, that doesn't prove that the one below it doesn't converge as well, right?
That's right. It does you absolutely no good because it's indeterminate. That's right. That's why you need the other one to converge. So what we're looking at is this. We're saying that we have a situation like this. Okay. If this guy converges, this has to converge also. But you're absolutely right. If this diverges, it's indeterminate. But the reason why I did this was because, and here's the thing, I don't know 100% what's going to happen. I'm testing this out. Okay. So I know that, that's 3n plus 2, right? I don't know why I wrote 1. So, I know that this guy is bounded above by 1 over 3n. I'm going to try that, see if it works. It might not, but that's going to be the quickest way to do it, okay? Okay, so here's how I'm going to start off. I'm going to start off using the comparison test. So I'm going to make the observation that 2n plus 3 times 2 to the nth plus 3 over 3 to the nth plus 2 is less than 2 to the nth plus 3 times 2 to the nth plus 3 over 3n. Okay? And now what I can do is I'm going to split these guys apart and I'm going to look at the leading term. Okay, I'm going to look at this series now. Does that make sense? Is what I'm saying making sense though to everyone?
Yeah, that makes sense.
Okay.
So once we grab the largest terms, know which one we're looking at, that's where I lost you. I don't know why.
So here's
why you.
Right. So here's kind of the basic idea. It's kind of like if you're fighting 4 guys, right? If you can take the strongest guy out, you can take the other 3 guys out, right? Okay. Same thing here.
Mhm.
This is the strongest guy. This is the guy that's the largest. If I can prove he converges, then all the rest of them automatically converge because they're weaker. They're less than him.
Okay.
Okay?
Well, why do we look at the original one?
Now, when you say original,
When
are you talking about when I replaced the 3n plus 1, or are you talking about the original, this whole thing here? It's 3n plus 2, by the way. When you say original, which one are you talking about?
the unexpanded one, the one that we started off with, you wrote it was less than the regular 3.
Right. So
Like
I wrote
the most,
yeah. And here's the reason why. Because no matter what sort of test I use, the ratio or the root test, this is going to be hard to evaluate, but this is going to be easy to work with. Okay? So I want to bound this out by something that's easier mathematically to work with. I know I'm going to have to use the ratio or the root test. And I know that's easier to work with 3n, 3 to the nth rather than 3 to the nth plus 2, okay?
Okay.
Okay, now I'm just going to look at the leading term here. So the leading term from this one is 2 to the nth over 3 to the n, which is 2 times n times 2 over 3 to the nth. Okay? So I'm looking at the leading term here. This is now, if you want to, you could call this a prime n. Okay, I'm looking at this. So I'm looking at just this series now. N equal 1 to infinity, 2 to the nth, 2 over 3 to the n. I can prove that converges, right? I can prove that converges using either the root test or the ratio test. It doesn't matter. You can do either one. This is relatively straightforward. I can show this converges using the root test or the ratio test, either one. So I want to reiterate one thing, which is comparison test is very, very powerful. It lets you take something that looks really nasty and turn it into something that's really simple. What I'm doing is I'm using the comparison test twice. I'm using it here to replace this with this, and I'm actually using it here just to look at the leading term. Saying that I only have to analyze the leading term, and if this converges, all the rest converges, is basically invoking the comparison test. How are we doing, guys?
Man, I think that all makes sense to me.
So here's the thing, and this is one of the reasons why I said I'm more than happy to have a problem-solving kind of like jam session, because the reality is that you learn a lot doing this by experience. And when I was a student, quite honestly, I think I did it kind of, I won't say in a stupid way, but I think I did these problems in a rather naive way, just knowing myself. I probably did not use the comparison test a lot, and that was to my detriment, I'm sure, because trying to use the root of the ratio test on this is actually not so easy. I mean, imagine trying to evaluate all 4 terms of the root and ratio test. You can do it, but it's incredibly complicated. But this comparison test, basically using the fact that if you can bound something above by a series that converges, then you automatically know this series converges, and using the fact that if you only analyze the leading term and it converges, the other ones converge, which is, again, invoking the comparison test, is a very, 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 very straightforward thing. Notice it takes me literally all of, although I didn't run the root and the ratio test, they're actually really easy. I mean, if we run the ratio test, it's this, right? 2/3 to the n plus 1 over 2n to the 2/3. This cancels. I have 2/3 on top, right? The 2's cancel. I have n plus 1 over n. Limit as n goes to infinity is 1. Okay? So it's very, very straightforward once you see how to do this. But again, this is why problem solving sessions are good, because thinking this through takes a little bit of time, okay? It's not something that comes to most people naturally, I don't think. Certainly didn't when I was a student, I'm sure. Okay, but I'll just also reiterate, if you don't feel comfortable with that, you can do each of these. Each of these would end up being, a ratio test. You can use a ratio test on all of these, and you'll prove that all of these converge. Okay. So you could do the ratio test on the leading term, say that it converges, and then by the comparison test, all the rest of them have to converge too. All right. If you don't like my fancy tricks, okay, you can do it that way too. Should we move on, or are we all good on this one? Yes.
Yeah, I'm good.
Okay, I'll take that for an implied yes. Okay, last one. Okay, when you have factorials, what do you always try?
Ratio test.
Always. However, if I kind of look down the road a little bit, I would realize I can simplify this a little bit, right? And here's what I'm headed to. N plus 2 factorial. This is equal to 1 times 2 times ... times n. Blow that up a little bit here. Times n plus 1 times n plus 2. Everyone feels comfortable with n plus 2 factorial, what that means?
So a regular factorial is like 1 times 2 times 3. And then you're telling me that this one is n times n plus 1, n plus 2?
Well, this is a set of this is a set of instructions. It says start at 1 and multiply all the natural numbers up to whatever this is. So it's 1 times
Okay,
2.
so it just means like we keep timing and until what that number is.
Bingo, exactly. Yep. Some people actually write this. I'll show you this because this is kind of clever, but you don't have to know this. You know, we have a notation for summing things. There's also a notation for products. This is called a pi product. This says multiply, and instead of, so when you write something like this, right, I equal 1 to n plus 2, this is saying sum everything from I equal 1 to n plus 2, right? This is saying multiply, pi for product. Multiply everything from 1 to n plus 2. That's another way of writing factorials, okay? Kind of cool. But notice if I wrote this over n factorial, what's going to happen? I'm going to get me a lot of cancellation, right? So notice that I'm going to get a lot of cancellation here, right? In fact, everything's going to cancel except the n plus 1 times n plus 2, okay? So even though you don't have to do this, it helps to simplify it. So I'm going to simplify it, and when I do, I'll get the following. And so here I have an n, and then I have an n plus 1 times n plus 2 left over, right? From my cancellation. Okay? Now,
Actually, I don't see why n plus 2 factorial has just a singular n multiplied by n plus 1 and n plus 2.
so if I go back to the definition of n plus 2 factorial, right? Make sure I'm answering your question here. But I'm multiplying everything up to n plus 2, right?
Yeah, I get that. I don't see why that n is there.
Oh, I think this was part of the problem, the original problem.
So and that n gets canceled by the lone n factorial.
No, the n factorial here cancels with a lot of the factors from the n plus 2 factorial. So
Okay.
Notice that the n plus 2 factorial contains n factorial. In other words, it multiplies everything up to n, and then it goes further and multiplies n plus 1 times n plus 2.
Oh. So then after those cancel, that singular n is still left there.
It is, yes, exactly. He's just hanging around. Okay, now, so who wants to kind of think about how we might approach this? What do you think? Notice that the root test is out of the question. The ratio test is going to be hard, right? But again, think about, so both the root and the ratio test are going to be difficult. If you try to apply the ratio test, it's not so obvious what's going to happen, because and here's the reason why the ratio test is so hard. Let's just try it. The ratio test will give us the natural log of n plus 1 over natural log of n times n times n plus 1 times n plus 2 over n plus 1 times n plus 2 times n plus 3. Okay? This is what the ratio test is going to give us. This is all going to evaluate to 1. When I look at the leading term, I have n cubed over n cubed. This, it's not obvious what it evaluates to. We've never talked about this. So this ratio is really hard to evaluate, okay? And it turns out that when you do this, this actually evaluates to 1. Even when you do this, it evaluates to 1 if you know how to evaluate this. So even if we did know how to use the ratio test, it would still be indeterminate, right? So what could we do to help us here? So here's another little trick you can use. I mean, it isn't a trick, but there are things that help you, okay? It's the fact that natural log of n is less than n. So I'm going to use some facts here. I'm going to use the fact that the natural log of n is less than n. Okay?
What can that n be? Like any number?
Exactly. This is true for all n. For all natural numbers n. And you can convince yourself. If you take your calculator, take the natural log of 25, it's always less than 25. It's even true for 1. Natural log of 1 is 0. It's less than 1, right? So now I'm going to use the comparison test. I'm going to use that the natural log of n times n over n plus 1 times n plus 2 is less than n over n times n plus 1 times n plus 2. Okay? And I'm going to look at the convergence of this. I'm going to see if this converges. And if it does, the comparison test tells me that this has to converge also, right? So let's look at this new series, okay? This new series has the term, I can cancel out the n's actually, right? 1 over n plus 1 times 1 over n plus 2, okay? When I sum this infinite series up, does it converge? This is my new infinite series, right? Does this converge? And the answer is yes. Anyone want to kind of think about why that is? So here's
Is this like a telescope or something?
okay. So the one answer is yes. You can write it as a telescoping series. Telescoping series are actually relatively rare, to be honest with you, but when you see them, they sure are nice. Because I can write this as 1 over n plus 1 minus 1 over n plus 2. And now the game is
I
over.
thought it was.
Okay, and now the game is over. A telescoping series always converges. It converges to the first term evaluated at the lower limit. And the reason why that is that's the whole point behind telescoping is terms keep canceling out, right? And sure enough, this actually converges, and you know exactly what it converges to. It converges to 1/2. Okay.
If you don't mind, could you just go back in time 5 minutes and explain?
Can you say that again, please?
Go back in time 5 minutes and explain what you had written. Past the point that we eliminated the factorials.
Okay, so here's the idea. What I did was I got to this guy here, right?
Mm-hmm.
And I want to figure out if he converges. So what I'm going to do is I'm going to try to fight a stronger person. In other words, the stronger series is a series where I had a series where the terms are actually greater, right?
Okay.
If I could show that series converged, if I had a series where the terms were greater than this and this converged, this has to converge also, right?
Oh, yes, that makes sense.
And so that's what I did. This is a very, very, very useful fact. Okay, I'll put 2 little stars next to it. Okay. Because this is a situation where neither the root nor the ratio test are easy to use, and even if you know how to use them, they're actually indeterminate. They actually cannot answer this question. So this is how you want to do it. Comparison test, okay? So then when I use this other series, this is the stronger series. If I can beat him, show he converges, I show he converges, and now I'm here, okay? Now, suppose you didn't see telescoping, okay? You can also use another comparison test. Suppose you didn't realize this is a telescoping series. You can use the fact that this is less than 1 over n squared. Okay? And this is a p-series that converges. So notice that the quantity n plus 1 times the quantity n plus 2 is always greater than n squared. So when I flip them, the reciprocal is going to be less. And this is a p-series that converges because p is greater than 1. Okay? So if I was doing this, even though telescoping is kind of slick, I will admit, I would probably directly use comparison. I would use a second comparison test and use the fact that this is a p-series that I know converges. This is how I would do it. Although I have to admit, I like this one. It's kind of cool. Okay. All right. So we've worked through all the problems. I'm gonna hang around till 3. If you have any other questions, feel free to ask. I'm gonna stop the video now